Okay, it's 2:40, so let's go ahead and get started. We're going to try to get through everything today that you should need to complete assignment 9. It's going to be a bit full again today to be able to hit that target, but hopefully we'll be able to do that, as well as make some larger points besides just going through calculations. Okay, so in terms of the things that we'd like to get across today, how many people have done cash flow diagrams in finance before discounting? It's maybe 10%, 20%. I'll include the people who aren't here right now. That's a pretty low number, actually. 10 years ago, actually students knew more about this than it seems like you haven't learned it in high school. You could have very easily learned this in high school. But the question is, if you want to make, you have a certain standard of living when you retire, how much money do you need to put away now? If you want to buy a car and you want to put a constant amount of money away, how much should you put away? This affects the environment as well, because when we talk about addressing environmental concerns, we're also talking about investing money today to receive benefits at a future time. So we're talking about money today, money in the future, how to connect them. And remembering that sustainability is really about the future, that's something we need to be able to do. Remember, environmental sustainability is when economics and the environment are working together, and sustainability proper is when the social dimension lines up as well. So really we're going through finance because this economics piece is so important. We talked about overconsumption, supply and demand last Thursday. You have a couple of problems on your homework, the first two problems that deal with that. Today, hopefully, we'll be able to have enough under our belt to be able to finish the rest of the homework. So we'll have to move. Okay, so some of the terms we hope you'll understand today. Cost-benefit analysis, life cycle cost. And then a bunch of terms like levelized annual cost, cost per unit product, average cost effectiveness, marginal cost analysis, payback period. And the reason we want you to understand all these terms is because, let's suppose that, you're somebody who's got a new green technology, and maybe I'm a status quo guy because I'm making plenty of money and, I'm not too interested in your technology. And you want to come to me and convince me that actually your way of doing things are better. Maybe you want to go to the EPA and say that, financially, your way of doing things is better. Now, maybe I go to EPA too and say, you know what, that way of thinking is a bunch of baloney, because on a marginal cost analysis, pick your term, my technology is better, right? These are different ways to analyze the financial characteristics of different technologies that we might be investing in today. And we want you to be able to understand what these are and hopefully come out of today understanding that really the gold standard here is to be able to compute a life cycle cost in terms of net present value, which allows you to do things like cost-benefit analysis. And some of these other things are useful, and when you go out, it doesn't matter if you're doing sustainability or not. You're going to hear these terms out there because they are bases on which companies might make decisions, okay? And also, we want to come back to risk assessment, too. You've talked about it earlier in the term, but now when we're talking about the financial piece, I think it becomes a lot clearer. Okay, so why does time equal money, at least in the world of finance? Let's take a little vote, okay? And you looked at this on your worksheet. So let's suppose I'm really hard up for cash. I need $100, and you've got $100 that you're willing to consider lending me. So, okay, you're thinking about lending me this $100. How much would you want me to pay you back in 1 year's time? Okay, so you give me $100. How much do you want back in a year? Who's willing to take $105 back? Got a small few. $110. All right, so $115. More than $115? That's the vast majority, okay? So the vast majority has a discount rate higher than 15%. Okay? I want you to think about what that means for sustainability. It basically means the future is screwed, and I'll prove it to you. Okay? It doesn't mean that you're the ones doing it, but it's actually a very natural consequence of the kinds of discount rates that we might apply. So for a company, you know, like a required rate of return, which you can think of as like a discount rate, they may be 30 or 40%. So it's not like, you know, those of you who got a high discount rate are that unusual. Okay, but we need to understand what the consequence of high discount rates mean, or discounting at all, means for future generations. It's not good. All right, so there's a couple of terms here. So the language I'm going to use, I know about maybe 10% of you have seen these cash flow diagrams before. So for those of you who might have seen this in different terminology, what I'm going to use here is $P being a present value, and $F being a future value. And the key is to connect future costs into present costs, or future benefits into present benefits. Okay, and the discount rate is what allows us to do that. And the reason there's a discount rate at all, and I kind of went through the last slide kind of quickly, but basically there's at least three factors, right? You know, $1 tomorrow may be worth less than $1 today because of inflation. There may be some risk that I don't pay you back. There may be, you're providing a service, right, by giving me $100, so you can think of that as rent. I'm renting your $100. You should be paid for that service. You should be compensated. You add it all up, you know, maybe you got a discount rate of 15% or more, right, like many of you had. So we're connecting future cash flows to present amounts through this discount rate R. And R has a bunch of different names. Some people call it the interest rate, but actually it's more than just interest rate you could get from a bank. It could be called the opportunity cost of capital, because you know, you're giving me $100 instead of using that $100 toward an Xbox or something else you might want to do with it, investing in stock or whatever you think could be a better return than just giving me that money. The hurdle rate, the required rate for risk has all kinds of names. So we're going to use the discount rate here. And again, we're just connecting future and present values. A cash flow diagram might look something like this. So what you do is you take future time periods and you put them on an x-axis here. And so these could be years, but they don't have to be years. So this is the first year, for example. It could be the first month. But your discount rate needs to be expressed in the units of this x-axis. So the present time is always time 0. And payments come in at the end of the year. So this is the end of the first year, the end of the second year, the end of the third year, etc. So we can put a present value on. We can put a future value on after n time periods. So we use n for the number of time periods in these calculations. Another definition here is annuity. So an annuity is a constant rate of payments coming in every period. And that's special. We call it an annuity because we're going to have a formula not only to connect F to P, but to connect A to P. And the parameters in these equations is going to be the discount rate R and the time period N on which that discount rate's applied, okay? So we can talk about annuities, constant payments over n time periods. And finally, we can talk about interest, which is an equal payment over an infinite number of years. Okay, so if I put $1,000 into the bank and I'm making 10% interest, which would be a really good interest rate at a bank, you'll never get that. But that'd be $100 a year. And that'd be $100 a year forever. It's not defined as a fixed time period. So you put money in the bank. Maybe some of you have an interest-bearing checking account or a savings account. that interest rate you have on that account is not specified in time. It's actually over an infinite number of years. So our fourth definition here, $I, think of that as an infinite annuity. Okay? So just baselining ourselves with some jargon, some terminology. Any questions so far? Yes? There is. The formula will be different. And I'll actually give an example to show how they're different. But, you can imagine, like, if n is 2, and you're giving me, $100 a year, over 2 years. Let's say the discount rate's really low. Over 2 years, it's about $200. It's going to be a little bit less than $200. But if you're giving me $100 forever, it's probably going to be a lot more than $200, right? So you're going to have a different formula for A than you will for I. Make sense? Other questions? All right, I went through that fast because we want to get to the fun part. Did all that make sense? I'm not going to bother deriving the formulas. I've done it in the past, and that's taught me that you're not interested generally. But it's fun to understand where these formulas come from. I think this one should be fairly obvious, relating the present value and the future value of payments. And the factor that relates the two is just 1 plus R over N. So if you think of one time period, and R is the discount rate, N's the number of time periods, right? And I multiply, let's suppose I'm making, let's use our same example here. We've got a principal of $1,000, and the discount rate's 10%, and I've got one time period. 1 plus 0.1, that's 10%, is going to be 1.1. And after 1 year, I'm going to have $1,100 because I made $100. Right? So this one's fairly straightforward, and that compounding factor is going to be to the power n. So if you have 2 time periods, it's going to be squared, and etc. Okay, so that's the formula. So let's take a vote now. Who would rather receive $300 in 4 years rather than getting $500 in 11 years, supposing your discount rate is 8%? Now, some of you had a discount rate of 8%. Most of you had a discount rate much higher than that. But keep in mind that this is an 8% discount rate. How many people would, I know you could compute it, but that's no fun. And I'll give you the answer in a second. How many people just off the cuff would take option A? I said almost everybody. How many take B? We'd have some B people. At 8%, you would find that they're almost the same. $7, it's about 3% error there, something like that. Okay, so they're roughly equivalent. Yet, just about everybody took A, and, that's again a reflection that your discount rate's higher than 8%. All right, the higher your discount rate is, the more you emphasize the present. So, $300, you can taste it. It's only 3 years away. Right, so that's indicative, again, of a higher discount rate. But actually, at 8%, they're roughly the same. Okay, this is just to give you some sense. Okay, and I know you all can do formulas, so I'm not going to beleaguer that point. But what I do want to do is just show you 2 plots here that show the effect. This is a 3% discount rate over different time periods. So the present value is $100. So at 3%, that $100 is only worth $55 in 20 years, and in 100 years, it's only worth $5. And this is a low discount rate, 3%. Right? Your discount rate was 15%. So look at this only goes up to 6%. You're like way off the chart. You're like halfway to the CSE building on this chart, right? When you talk about a 15% discount rate. But look at what $100 is worth in 100 years, at just a 6% discount rate. Remember, we just looked at an example of 8%, and you all have a higher discount rate than 8%. It's a 6%. It's only worth 20 cents today. So what do you think about sustainability? Is that a 1-year issue or is it a 100-year issue? 100,000-year issue? Right? So what does this mean for sustainability? Help me out. Yeah, and the future is almost literally worthless. Right? Companies make decisions this way. And we make decisions this way. Right? This is all about allocating resources, energy resources, material resources. It's sobering, right? Let this one soak in, right? This is the basic point. I mean, we can play with problems, but it only took me 5 minutes to make the point. How many people feel like they understand the point? That's most people. Anybody else want to ask a question? So let me try this another way. I mean, you must be thinking, well, wait a minute. I mean, these resources do have a value in the future. Sustainability does have a value in the future, right? The access to resources, a stable climate, right? Materials, what have you. Can't we just place a high value on it? Then it will have a high present value, right? I mean, that makes sense, but the future doesn't have a voice, right? So let me try to drive this home, all right? So 5 years ago, I didn't have kids. Today, I have 3 kids. If you'd asked me 5 years ago, like, what's the value of your kids? Like, how could I have answered that, right? I mean, it's like, they weren't here. It's like, I couldn't jump in the year, 5 years in the future, right? But if heaven forbid I lost a kid, or what price would I be willing to pay to save one of my kids, right? I'd be willing to give it all up, and anybody would, right? And, that's how the future is going to feel, right? But, we're not in the future to be able to express those values, right? And to make that case, right? So, there's a real problem when it comes to trying to preserve quality of life and not overconsume in the present. There were 2 factors here, right? One factor we talked about last Thursday is that when we look at supply and demand and we look at the costs we see, we tend to overconsume because there's always costs we can't see, and many of those costs are to future generations. Furthermore, those costs to future generations, when we think we can substitute those costs like we can substitute money, right? You can't substitute having a kid for not having a kid, right? It doesn't work like that, right? And there are obviously a lot of things you can't just place a financial value on, and it's not like a liberal, green agenda. It's just the way it is. It's the way the world works. So if we think about sustainability, then we got to think about, okay, well, what's it actually going to mean to not have a stable climate? And are we going to, just let simple discounting rule our decisions today? Do we really have a sense of what those costs are going to be in the future? That's the philosophical point here. But it shows up in a lot of ways, not just in the way we treat the future, but even decisions we should be making in our own best interest today. And I'll bring some examples here to drive all this home. But, this is, I could end the lecture now. I mean, this is pretty much the point. But it wouldn't be any fun without giving you some skills to make some calculations. Any questions? Yes? In this case, it is, think of it this way. Like, I'm afraid to put money in the bank, so I have $100, I'm just going to put it under my bed. So I forget about it for 100 years. And one of my kids, hopefully, sweeping up my bones or doing something, oh, here's $100. And they go to spend it, and actually, the buying power of it's only 29 cents. That's all this is. But of course, like that's inflation because a dollar is worth less in the future than it is today. Obviously, we could have done other things with our money, so there's opportunity costs as well by not spending that $100 or investing that $100, right? So that's why this discount rate exists, and it makes sense. But when you flip it around and say, okay, well, the future is going to have some cost that we can't even imagine today. First of all, because money is worth less in the future. But second of all, it's because they don't have things that we have today, right? Unless the things that like a stable climate can somehow be substituted, or the access to material resources or energy resources can be substituted evenly, right? A lot of times we take it on faith that can happen, but in a world of 9-10 billion people, there's nothing saying that. Right? Nobody can guarantee that. So we can talk about risk. And we will just in a few minutes, hopefully. Are there other questions? All right, I think I got your attention. I mean, this is a big deal. Let me drive this point home further. So suppose that you've got a discount rate of 8%, and I'm going to give you $75 forever. What do you think that's worth in terms of present cost, present value? $75 forever at a discount rate of 8%. Well, we need the formula for interest. And that's basically it's called ordinary interest. But basically, it's just the principal times the discount rate. So if the principal is $1,000 and it's making 10% as interest, or the discount rate's 10%, well, that's going to be $100. That's going to be your interest. So this is the relationship between I and P. I haven't given you A and P. I gave you F and P before, and this is I and P. Okay? So I can just rearrange the equation and get the present value if I is $75 and R is 8%. So if I go ahead and do that, then the present value at 8% of receiving $75 forever is $937.50. Now, be honest, how many people would have taken the $700 today? Yeah, I'm guilting you into it, but I would have taken it too. I mean, come on, we're human, right? I mean, so you could buy a new iPad with that, or whatever. $75 forever just doesn't seem that appealing, right? Compared to $700 in your pocket right now. And I'll bet if you go on the sidewalk out here and you ask 10 people would probably take the $700 right now. Now, part of the reason for that may be, well, you're thinking about, well, I'm not going to live forever. Maybe you all got another 75 years left in your life, so maybe it's not going to actually be worth $937. It's going to be actually worth a lot less than that when I only look at the first 75 years instead of looking at forever. So how many people think that it's going to dip below $700 if I only look at the first 75 years? Remember, if I get $75 forever at 8%, the present value is $937. Okay? So my question is, instead of that $75 forever, you only get the first 75 years. So how many people think that the first 75 years are going to be worth less than $700? How many people think it's going to be worth more than $700? Okay, so you're starting to get the point, which is fantastic, right? If you actually do the calculation, and this is the formula now that connects A and P, And that factor, by the way, is often called the capital recovery factor, because if I'm going to invest $1 million in equipment, and that equipment every year is going to give me some annuity at 8% over, pick the number of years, 40 years, A would need to be the capital recovery factor, the amount of money I'd need to make each year to get my $1 million back. Okay, so this connects the annuity to the present value. 1 plus R to the n, quantity minus 1, the discount rate R times 1 plus R, quantity to the n. Okay? So if we look at getting $75 every year for the next 75 years with an 8% discount rate, it turns out that that's worth $934. Right? So basically, that $75 forever is about $937. And the first 75 years is $934. So that means that the infinite number of years from year 76 on is only worth $3 today. Right? So what's that saying about the future? Anyone? Yeah, exactly. So, investing in the long-term future is bad economics, is bad finance, right? Right? Makes sense? Unless you can prove that you're just going to make a bazillion dollars in the future, but who's speaking up for that future? How would you prove it? There's risk there as well, right? And high risk. So sustainability, you can think about it. It's like anti-discounting, right? So think about what the world would be like if we took a 100-year view, or even a 10-year view. And we've done that forever. Think about all the gains that we would constantly be getting because the people before us kept thinking about the future. Right? Instead of putting debt on the future, whether that's environmental debt or whether that's debt of a government, right? Passing on debt to future generations because we're spending all the money now, making commitments now, whether it's the healthcare system, whether it's defense, whether it's retirement, whatever it is, Medicare, what have you, right? We said, we're going to, look at this different. Not only are we going to run surpluses, but we're actually going to make investments that actually help our kids. And we're constantly going to do that. Right? You'd be, constantly, in a pretty good position, right? If the people before you had done that. So think about, like, the roads. This is a good example, right? So, roads have all kinds of potholes in them, and you can actually calculate how much cost drivers lose because they're getting flat tires and things like that, and the roads being big enough, wide enough, what have you. Traffic congestion is a big cost. Construction, how many times have you been stuck in construction, right? If you just built the road right so it could last for 40 years, like they do in a lot of European countries, you'd have less construction, right? You'd spend less time in traffic. You'd be getting from here to there faster, and there'd actually be a value to that, right? That's just one example. Right? Instead, we don't make our roads that way. We tend to do it on the cheap, and we pay for it constantly, right? Sustainability, you can think about it as anti-discounting, right? So this was a picture I took yesterday. These are my kids at the museum. And what I liked about this one was that this is the frog and toad croaks. So different types of frogs and different noises they make. And my kids were crazy over this, right? But I realized, when's the last time I'd heard a frog croak, right? And I grew up in the suburbs of Chicago. There were frogs everywhere. We could catch frogs. And, with land use changes, right, and you can then think about, there are some things going on with frogs in the world. And if you're interested, you can look up the information on that. But, they're probably going to have less access to frogs, Maybe they care, maybe they don't. They probably don't. You can call it progress or what have you, but they may be stuck with a machine like this to hear, a bullfrog croak or what have you, right? Anyway, they seemed interested in it. But the point is, they don't have what if the croak of a toad's worth something in the future we couldn't know, right? Or maybe there's a medicine, right, that, or some genetics from frogs that we can learn about. And some specific species in the rainforest is going to be gone before we figure it out, right? So we can talk about the preservation of diversity, biodiversity, right? So, sustainability can look a lot like anti-discounting, right? It's good karma to pay it forward, right? And that's basically what the message is here when it comes to sustainability. But, you don't have to think about anti-discounting to be on the side of sustainability. You can just do what's good for us in the here and now. You hear a lot of gripes from industry about the Clean Air Act. The Clean Air Act regulates 6 criteria pollutants. Oh no, part 1 of the class. Actually, 7 criteria pollutants. What are they? Anybody? Just shout them out. Clean Air Act, so they're air pollutants. Go ahead. NOx, NO2, nitrogen dioxide, sulfur dioxide. Sorry? Ozone. Carbon monoxide. That's 4. Particulate matter, and that's 2 because it's 2.5 and 10.0. Lead, and I'm missing one. What would it be? Oh, no, I miscounted. We got them all. Okay, good. All right. So now the Clean Air Act restricted ambient exposure to these air pollutants. Okay? So, and I haven't listed what they are here. But basically, if you're the city of Chicago, the great city of Chicago, and you've got nitrogen dioxide concentrations that are too high or sulfur dioxide concentrations that are too high, you're supposed to come up with a plan to fix it, and money isn't supposed to matter. And if you don't fix it, you're a non-attainment area, and that's supposed to be a bad thing. I mean, in the end, most urban areas are non-attainment zones for these criteria air pollutants. But despite that fact, there has been much improvement since the Clean Air Act amendments of 1990. And this is looking at what those benefits are. So if we look at, these are real benefits in the year 2010, given actions we took in the Clean Air Act amendments of 1990. And the big one here is just reduced mortality. People living longer because they're breathing clean air, with an estimate of being $100 billion a year. Right? Now, if somebody else dies of a heart attack because they were out and the particulate matter concentration was high and there happened to be sulfur around at the same time, so it sent them to the hospital room, and unfortunately they didn't make it. Like, there's no way to say, like, oh, bad air did that, right? Just like the Texas drought last year, you can't say, well, that was climate change, right? It's hard to just point to it. But the fact is that statistically there was a higher probability of that happening. And when you do the statistics on it, bad air sends a lot of people to the grave early. And in 2010, the benefits of actions taken in the Clean Air Act amendments of 1990 were worth $100 billion. Now, there's a lot of other benefits here too, but in aggregate, they're only worth $10 billion. So that the Clean Air Act amendments were worth about $110 billion in 2010. Now, how much do you think we spent in 2010 on the Clean Air Act amendments to abate that pollution? Who wants to venture a guess? $1 billion? How many people think it was more than $1 billion? Okay, more than $10 billion? More than $50 billion? Okay, nobody. I think you're in the right zone. So when you actually look at it, you can go to the EPA website just like I did. What you're looking at here is population growth, where my laser pointer here is, population growth and energy use growth. You're looking at an increase in private sector jobs. You're looking at an increase in vehicle miles traveled. You're looking at an increase in gross domestic product. And you're looking here at the emissions to the air of these criteria pollutants. So, we've had more jobs and job growth while we have reduced criteria air emissions by about 60-some-odd%. The cost of which was about $26 billion in 2005. Okay, so we're at a range of about 5 to 10 to 1, probably closer to 10 to 1 in terms of the benefits. So you think about it, okay, well, if I put in $1 and I get $10 of benefits back, that's probably a good deal, right? And that's what investments in the Clean Air Act have brought. Okay? Now, this is not to say that everything you can do for the environment is a good idea, because there are financially smart ways to protect the environment and there are financially stupid ways to protect the environment. So we can think about both. But before we do that, this is just an example looking at the benefits and costs of emission standards for non-road diesel engines. Okay, so basically you can look at, these are, in this case it's NOx, SOx. Let me make this bigger so you can actually read it. So we're looking at proposed reductions from 2007 to 2030 in the regulation of NOx, sulfur dioxide, non-methane hydrocarbons, like VOCs, particulate matter. Okay, and we're talking about reductions of, in the range of, I guess, 30 to 97%, depending on which air pollutant we're talking about. So we're talking about non-road diesel emissions, like construction equipment, certain recreation vehicles, okay, lawnmowers. Okay, and if you look at, if we look at that, here's your cost-benefit table. Okay, your reduction in premature deaths in doing this is going to be about $39 billion of benefit to about $1 billion in cost. Now, part of this cost is going to be changes to engines, diesel engines. Part of this is going to be eliminating sulfur from diesel fuel, and those costs were included here. That's a pretty good benefit-cost ratio, 39 billion, or 40, actually when you add it all up, it's 43 billion to about 1.4 billion. Right, that's pretty good. Right? But suppose you're the construction company that is in the market for a new bulldozer, and that new bulldozer is going to cost you 10% more because of this law. Are you going to be in favor of this law? Probably not, right? Even though the benefits accrue to society, right? This goes back to the tragedy of the commons, because the benefits and costs are allocated to different folks, right? So if I'm a powerful construction mogul, and every new bulldozer, every new piece of equipment is going to be incrementally more expensive, maybe I'm going to fight hard and I'm going to try to influence politics because this is really bad for me, right? Even though maybe I've got a mansion and what have you, right? I'm just looking at the bottom line and I'm just doing the discounting, right? So this is cost-benefit analysis now. The costs are a heck of a lot easier to add up than the benefits are. And the benefits don't have a voice unless EPA does it. Right? And EPA tries to be as conservative as they can in their estimation, but maybe it's just easier to demonize the approaches that they use to try to estimate these costs. Right? But they've been backed up in the literature. It's not just the EPA, it's science in general. Benefits and costs, and benefit cost analysis. Trying to give you some examples so you got a feel for what it is. You'll do some of this in your homework. Any questions? I know you can add up costs, and I know you can add up benefits, right? This is just, it's not even algebra, it's just arithmetic. Gets a little bit trickier when we've got discount rates. So you need to use these formulas that relate future value to present value, annuities to present value, interest for an infinite period of time or an infinite annuity to a present cost. But you can do all that. Just do a free body diagram, and just like you do in physics. You always make the free body diagram. In this case, you always make the cash flow diagram. Okay, and as long as you do that right and you apply the formulas, you're going to get the answers right. So what I tried to do, instead of beating the point to death, what I thought I would do is try to make this interesting. So let's first look at smart ways to reduce pollution and maybe some of these dumb ways. So this is, remember before we were looking at non-road diesel emissions. Here we're looking at different projects to reduce NOx emissions in Southern California. So this was done by the South Coast Air Quality Management District. Okay, and they looked at, this is dollars per pound. So this is like a cost effectiveness calculation, right? So at $2.46 per pound of NOx eliminated, we can repower off-road diesel engines. Okay, and maybe that's a pretty good deal compared with implementing video conferencing on a grand scale in Southern California. Right? That cost effectiveness, it costs $22 for every pound of NOx that you save. That would be a bad thing to do. That'd be a dumb way to do it. Giving people free public transit passes, that's going to cost $74 per pound of NOx reduced. The reason is that people will probably gladly take their public transit passes and keep on driving. Right? So that would be a pretty dumb thing to do, right? So this idea of cost effectiveness, dollars to reduce some pollutant, that's one way we can make an evaluation between different strategies to address sustainability challenges, in this case air quality. We've done some work along these lines in my lab as well, and this is just looking at CO2 cost effectiveness in transport in particular. So we're looking at lightweighting vehicles. So suppose that I have 6% lightweighting of a vehicle with steel or 6% with aluminum. Well, the steel is going to turn out to be a little bit cheaper than aluminum. Now we can use a diesel strategy. We could use a hybrid strategy. We could use a plug-in hybrid electric strategy. We can think about, in comparison, the steel industry or the aluminum industry. Excuse me. What's the cost effectiveness in terms of lightweighting a car? How much do we pay up front versus how much CO2 do we save? So we can come up with an abatement cost, dollars per ton of CO2 emitted, just like we looked at dollar per pound of NOx reduced. Okay? So this is the idea of cost effectiveness, and it's a way to compare different strategies. Okay, and you've got one homework problem where you're asked, okay, well, here's a certain situation. Compute the dollar per pound of X abated. Which option looks to be cheaper on that basis? Cost effectiveness basis. Does it make sense? Now, one of the ways we could reduce CO2 emissions is to buy plug-in hybrid electric cars. Okay? So who can tell us what a plug-in hybrid electric car is? It's the one on the left. Come on, help me out. Does it use electricity? How many people vote yes? All right, thank you. Does it always use electricity? All right, so you know what a plug-in hybrid electric vehicle is. All right, so there's a little charge port, which you can't see in this picture. You drive it home at night after you use some electricity, and you plug it in, top off the battery. Battery holds about 40 miles of charge in the summer, about 28 in the winter. And if you drive really far, like 200 miles, well, that's more than 40 miles, so there's a gasoline engine that's going to kick on. It also carries gasoline, and it's going to then run on gas. So a plug-in hybrid electric car runs partially on gas. Partially on gas and partially on electricity. Question? It is. That's the next thing I was going to say. So this is my car, which I bought in December of 2011. I was never into having cars. I had a 15-year-old Honda Civic that was my wife's from graduate school. And this thing came out, and I fell in love. My wife's only a little jealous of my relationship with this car, so we're doing okay. But the current sticker price for this car is $31,600. These are all real numbers. In the first year of driving, I drove 8,600 miles. That's not a whole lot. A typical American's going to drive 14,000 miles. And basically, all these miles were taking my 2-year-old around town because she has a high travel demand. When I'm by myself, usually I'm riding my bike. I do have a startup company in Detroit, so I take some trips there. I don't usually take my bike there. And I think I went up to Traverse City once in this thing, too. So we have burned some gas in it. And overall, it's gotten 132 miles to the gallon. But when the car is running on gas, it only gets about 34 miles to the gallon. And that may seem kind of low. It's actually pretty good because the car is kind of heavy, because it's got a bunch of batteries in it. But it also uses gas to keep the batteries warm, so I actually lose a bunch of fuel economy on that. When I'm just running electric, I'm getting about 35 kilowatt hours per 100 miles. And actually, to this day, I've driven about 75% electric. I pay about 10 cents per kilowatt hour at home. So we can figure out how much, if I'm going to assume that I'm going to have this car for 20 years, because I do hold on to my cars, and I've got a 4% discount rate, which, in the interest of karma, tends to be the one I use. Does this having this vehicle make sense? Now, this was the only car I wanted, but I tried to put myself in the situation. Okay, well, what other car would I have bought that's something like this? So I picked the Mini Cooper. The Cooper S, because my name's Steve, and S and Steve go together, so I picked that one. The list price on that is about $25,450, so there's about a $6,000 delta here. The fuel economy, 24 miles to the gallon. I'm going to use a gas price at $3.76, and I'm going to apply that to the Volt 2, even though I'm going to probably put more expensive gas into the Volt than I would for the Mini Cooper. But I don't use a lot of gas in this, so it's probably okay to make that assumption. Okay, so somebody tell me, if I'm looking at the life cycle cost, here's another definition for you, life cycle cost. Looking at all the costs over 20 years, how am I going to do it? Let's start with the Cooper S. I think that might be easier. Talk me through it. What am I going to do? Good. All right, so I got $25,000 almost. I'm paying up front. And then so that's a cost up front. What other costs do I have to consider? Maintenance, which I'm going to ignore here. Maintenance will be higher on the Cooper than the Volt. unless they screw up the technology on the Volt. But it's actually been one of the most reliable cars on the market. Yeah, so we'll get into risk in a second. I think it's going to be about 10 years. I've got inside information on that, so I'm comfortable with 10 years, but have they actually come out and said it? No. Okay. Yeah, so either way, you got to pay for fuel. So we're going to ignore maintenance costs. I'm going to ignore the battery costs that I might have to pay in 10 years. My own personal view is if GM would give me a new battery for this car, the engine is hardly run. That engine, the gas engine, is going to be brand new. Everything on this car is going to be like brand new except the battery pack. Drop a new battery pack in it, instead of 40 miles, maybe I'm getting 80 miles. It's like better than when I bought it in 10 years, and I'd gladly pay them $7,000 in 10 years to do that. Just because, I think gas will be more expensive, and I love my car, and I would do that. So, paying more for battery packs, let's look at the numbers here. That actually might make some sense, depending on how the relative costs look. I got to discount the gas costs, right, or the electricity costs. So what I'm going to do is I'm going to add up the fuel I use in a year to go a measly 8,600 miles. So how much gas do I use? And then I'm going to apply $3.76 cents for every gallon I use. And then for the electric, probably I'm going about 6,000 miles on electric, and I use 35 kilowatt hours for every 100 miles, so I can figure out how many kilowatt hours per year, and I've got 10 cents per kilowatt hour, so I can figure out how much I'm paying in fuel, electricity and gas for the Volt, and in just gas for the Cooper. And I'm going to assume that's constant every year for the next 20 years. So how am I going to figure out the net present value of the fuel cost? What formula do I use? Go ahead. Yeah, it's the annuity formula. So I can do two things. One, I can get Excel, like a spreadsheet out, and I can just have the costs in there every year, and I can go back to the present value. But you're not going to be able to do that on an exam, so you'll want to use the annuity formula. Okay, constant cost over n time periods, applying a discount rate of 4% and a time period of 20 years, because the discount rate's 4% a year. Does everybody think they can pull out a formula and put numbers into the formula? I know you can do that. But what you need to know is which formula to use. It's the annuity formula. And you need to figure out, okay, well, how many miles on gas? How many miles on electric? How much does the electricity cost? All right, that's all algebra, and you all can do it. I'll show you the answer in a second, but I want to see if there are any questions first. How many people feel like they could do this problem if I said this is your quiz right now? I don't want to make this a quiz right now. Who's got a question? Exactly. So for the fuel costs, we're going to assume that we're paying a certain amount of fuel cost for each vehicle in each year. Now, it's a constant amount over 20 years, so I'm going to use the annuity formula to figure out the net present value of the fuel cost. Then I'll add it to the upfront cost to buy the car and compare the two. Let's take a vote. Under these assumptions, who thinks the Volt is more expensive over 20 years? Life cycle cost over 20 years. How many people think the Mini Cooper is more expensive? That's shocking to me. You think I'm rational? Like, I was in love with this car. Like, that wasn't a rational choice. And why do you think why do you think the people who thought the Mini Cooper is going to be more money? What's the basis for that? What's that? The gas is pretty expensive. It's $3.76. I actually took that to current value. Why else? Go ahead.
The electricity is really cheap.
Electricity is cheap, and the discount rate's low. right? If the discount rate were really high, if it was like 100% or something, like those fuel costs would just drop off immediately, and the Mini Cooper would be cheaper, right? And it turns out your instincts are excellent. So normally when I ask that question, people don't get the right answer. So I'm really, really pleased by that. So this is just going through the calculations. The fuel cost for the Volt is about $465 a year. You can check these numbers, make sure I got them right. The fuel cost for the Mini Cooper is about $1,300 a year. I use the annuity formula. And what I did here is, if I've got two things I'm comparing, and both have the same time period and the same discount rate. So the Mini Cooper and the Volt both have a 4% discount rate over 20 years. So why would I compute this number twice? When you're taking an exam, just remember that. If you're comparing two things, just use the same factor, right? So I went ahead and did it for the Volt, and that factor converting the annuity to the present value is 13.6 for a 4% discount rate over 20 years. Just use it for the Mini Cooper as well. And you are correct. The net present value, life cycle cost of the Volt is $38,000, and the Mini Cooper is about $44,000. Okay? So you're right about that. Now, there are other external costs, right? Question? I could do that, right? So maybe that's going to be $5,000 in 10 years. Let's say it's $5,000 in 10 years. Even if it is, right, it's actually still works out. Because that $5,000 in 10 years is going to be a lot less today, right? Now, if it's $10,000, it's going to be pretty close here, right? Now, there are other maintenance costs for the Mini Cooper that are likely to be higher that we're not accounting for either. Something else is I'm paying more for electricity than I need to. So this is something I didn't mention, and this is maybe idiosyncratic to my own situation, but looking at, I wrote 0.08 cents here plus 0.02 cents. So that 0.02 cents is actually so I can get electricity carbon offsets. So when I'm running on electricity, it can be guilt-free. It doesn't mean that I have wind power or solar power or biomass running my car, but the money that I'm paying for every kilowatt hour here, that extra 2 cents, are funding projects that wouldn't have happened anyway. So somebody else has carbon neutral electricity. So that way I can feel a little bit better about that gas. So actually, there's some inflation in terms of the electric fuel cost here as well. If fuel costs go up in the future, it's very likely that the gas prices will go up higher than the electricity. So, we could talk about risks. Maybe my battery is going to last longer because I don't put as many miles on my car, right? So, time's going to tell, and maybe it's a really bad idea and my battery is going to drop off tomorrow. I've had the car for a year and a half, haven't noticed any deterioration in the battery yet. So, knock on wood. Other questions? So, there are other external costs that this doesn't even include, like the cost of carbon dioxide to future generations, cost of NOx, right? These external costs, which I could, include in this analysis, and the Volt would look even better. And you're going to have a question on your homework that actually gets to that. Suppose that we include the external cost of NOx or the external cost of CO2, and we added it to the electricity cost, we add it to the fuel cost, right? How would this equation change? Right? Volt would actually look more favorable in that case. Okay, let me, you have these calculations on C-Tools. At a discount rate of 10%, your annuity to present value factor drops, which you would expect, right? Because future payments are worth less under high discount rates. So instead of a factor of 13.6, you've got a factor of 8.5 when I use a 10% discount rate over that 20 years. And it turns out, in that case, the Volt and the Mini Cooper look almost the same. You say, oh, well, then that battery cost is going to really tip the scales, but the fact is I used a 10% discount rate, so $5,000 in 10 years isn't going to be a whole lot of money here, right? So maybe I don't consider that if I've got a discount rate. So my question to you at the bottom here is, why don't people buy Volts? I mean, these things are not selling very well. Good. What's that? No, they don't. No, they don't. Yeah, they did a side impact test under a contrived condition that would never happen, and it caught on fire. This car, I park it every night underneath my twin's bedroom. So if I was really concerned about this, I wouldn't do that. So it's $6,000 more up front, and that's a barrier, right? Because people tend to have high discount rates. Yeah, they're used to it, but they weren't used to cell phones, and so suddenly they were used to cell phones, right? And people that I take around in this thing tend to want one. All right, so you can talk about information. Not a perfect market. But they're actually real factors, right? Think about what it means. Like, how many people would pay for either of these cars? Suppose you needed a car. These were the only two cars you could buy on the market. How many people would pay cash? It's okay to raise your hand. Like 2 or 3, I paid cash. Okay, like how many people would take out a loan? That'd be almost everybody else, right? Now, if you look at the per month cost for the loan, like you're talking about $530 a month versus something like $380 a month. Like that's a pretty big difference in monthly payment over 4 years on a 3% loan. So you say, oh, wait a minute, now I'm looking at this as a levelized annual cost over 4 years at 3%, and or I look at my loan calculator online is the other way to do that. And suddenly, wow, that looks like a lot of money, right? Because you don't pay the fuel costs up front, you just pay the vehicle cost up front, right? So it looks like a lot of money, even though you're paying more money in the longer run for fuel, and you have to pay off the loan. That's one reason, right? What's another reason why people might not choose the Volt? We already talked about technological risk, which is real. What else? Go ahead. Some people may pay more for electricity. Excellent. What else? Okay. Yeah, less choice. So if you just like dead set against buying a Chevy, like you're done, right? I mean, there's this plug-in hybrid that's out there, right? Or at least it was a year and a half ago. Okay. Say again, sir? So a pure electric car, that would be true. You'd need a really long extension cord, but this car runs on gas as well, so you can just go to the fuel station and fuel up if you have a business trip. Yeah, so I can't put all 3 of my kids in the back seat. There's a battery in the middle. I can only put 2 back there, which is why the other car we have is a minivan, which I never thought I'd be proud of, but boy, do I love that thing. Anyway, I'll get into that another time. Well, think about other things you might want. So there's a $6,000 difference between the Cooper and the Volt. Suppose I want to get, a premium sound system. I want leather, right? I might actually put some of that upfront money into that, right? And these are real trade-offs as well. Okay? And I'm certainly not trying to tell you how to make decisions, but I'm trying to keep it real here. And these calculations in your notes, if you go on to C-Tools, I basically have written all this out. Okay? Let's do one more. Light bulbs. Okay, how many people, let's say you've got a light bulb in your apartment and it burns out. How many people are going to go on Amazon and buy a $60 geobulb? We got one? Are you the jokester in the crowd, or you're not buying it? Pretty insane, right, to even think about that? These are real values, actually. So I actually went on Amazon and looked. All right, and we're going to assume here the power it takes from the grid is about 7.5 watts, and it has an equivalent luminance of about 60 watts. So now I go on to Amazon. I need a light bulb, and I'm not talking about shipping costs here. 60-watt bulb, a pack of 4 is $8. That's $2 a bulb. How many people would prefer that option? All right, looking pretty good, right? Okay, now here's the thing. This is an LED bulb, and it is going to last about 20 years at 4 hours a day. And this is going to last about 2,000 hours. Again, we're going to assume 4 hours a day. And we're going to have a 20-year lifetime. Okay, so we're going to look at the life cycle cost. Okay, so tell me how to do it. I mean, I have all the calculations, but tell me how to do it. How am I going to get the life cycle cost here? Not doing shipping cost here. So I'm going to pay up front for the light bulb on the right here. It's $2 up front for the light bulb, and then I have to figure out how much electricity it uses a year. And then I figure out the price of electricity. I'm still going to use 10 cents a kilowatt hour. Keep my carbon offsets there. I've got 2,000 hours of bulb, so then I need to figure out how often I'm replacing a bulb. It turns out that 2,000 hours, I'm going to use that at 4 hours a day in about 1.37 years. So every 1.37 years, I got to buy another light bulb. So I could buy a 4-pack right now, but I'm going to assume that I'm going to buy a $2 light bulb every 1.37 years. Is that going to be more expensive or less expensive than buying a 4-pack today? If I get the 4-pack today and I buy all 4 $2 light bulbs today, is that going to have a higher net present cost than spacing those $2 light bulbs as payments every 1.37 years? Who votes for spreading the payments out being more expensive? Who votes for buying all 4 light bulbs up front being more expensive? Okay. Buying them up front is more expensive. Right? Because of discounting, right? If I just wait to buy the other 3, then discounting means the net present value will be less. Everybody understand that? If I had the option of buying them one at a time, I would, and I wasn't thinking about shipping, I would buy them one at a time every 1.37 years. But there's a problem here because if I've got a 4% discount rate per year, what's my discount rate over 1.37 years? Uh-oh. Anybody have an idea how you might try to do it? If I have a 4% discount rate per year, and I need a discount rate every 1.37 years, what might I do? Go ahead. Well, you could do that. The issue there is really I think what you're getting at is proportionality, right? So, well, I'm going to estimate it over 2 years as being 8%. So 1.37 years, If I do the proportionality on it, it'll be about 5.5%, right? That's actually not correct, but it's within about 1% over 15 years, so it's a good thing to do. And so that's what we're going to do here. But you also have on C-Tools, I actually did this for you, how you actually should do it. Oh, you can't see that. All right. So this is just looking at a dollar up front, 4% discount rate. So it's $1.04 after 1 year, $1.08 and some change after 2 years, what have you. And what I did was I took a time period. So here's 1.37, and I'm just adding 1.37 to each year. And I found a year where they match. And then I say, okay, well, I'm going to just do the proportionality thing, and I've got a 5.5% discount rate. And, it's within about 1%. It's less than 1%, actually, in difference. So over 15 years, that's good enough, right? So you need to do equal time periods and then, trial and error to figure out the discount rate. And it turns out that proportionality tends to work. And you can do that for your homework. Okay, so I'm telling you can do that for your homework, but you may take that to another class and do the same thing. And some stickler might say, well, that's not actually right. But it's actually pretty close. Okay? This is actually the right way to do it. Questions about that? Everybody understand what they're looking at? Go ahead. Yeah, I actually did it from proportionality, so let me show you that calculation. It's here. A little hard to see. So discount rate of 4% per year. So 4% 1 year, X, and 1.37 years. So that's just proportionality. It gives you 5.5. So I tried that first. Over 15 years, it's within 1%, good enough. Now the other thing here, before we conclude for the day, is the proportionality factor. I'm sorry, the cash flow diagram, my bad. So this is how you do the problem, and this is how you do any problem with a cash flow in it. You make this diagram, and this is what we started with. So you've got the years on the x-axis in red. You've got a light bulb you're buying at time 0. You've got electricity costs every year. And then you've got bulb costs every 1.37 years. But if you've got the discount rate for the for 1.37 years, then you just need to figure out how many light bulbs you're buying. And it turns out you're buying 14 light bulbs. So you can look at N of 14, discount rate 5.5%, $2 a light bulb, and now you've got the added light bulb costs. So this is your first bulb, which you buy at time 0. This is for the incandescent bulb. It's $2. Then you've got a factor for the net present value of buying 14 bulbs. Since it's every 1.37 years, you've got a discount rate of 5.5%. So use the annuity formula. $2, discount rate 5.5%, N is 14. And then you've got the net present value of electricity each year. Does that make sense to people? The compact fluorescent's easy because it's just the upfront cost, and then over 20 years you use it, the electricity cost per year. Okay, we need to take our quiz. So as you're taking a sheet of paper out, let's take a quick vote. Who thinks the incandescent bulb is more expensive over 20 years? Who thinks the compact, this is actually an LED bulb, my bad. The LED bulb is more expensive over 20 years. Okay, I'll give you the answer. The incandescent bulb over 20 years has a life cycle cost of $105. And I called it a compact fluorescent. This was an LED bulb, so I need to change that. Was $75. So it's actually a heck of a lot cheaper to buy your LED light today and take it with you when you move. And I still have compact fluorescent bulbs from grad school 15 years ago. Still work. All right, I know we did this last part a bit fast, so we'll pick it up next time. Please place your name on a sheet of paper. Don't talk to each other. And please answer this question. Please list the primary challenge that discounting poses for intergenerational sustainability over time frames greater than 75 years. Just a couple sentences. You don't have to wax poetic like I did. And just answer the question, and then please leave quietly, and Vineet will be down here. He can collect your responses.